Steinmeier. A warm welcome also from me here at Fraunhofer IPMS. My name is Dr. Wenke. I'm the Deputy Director of the Institute that you are visiting here at the moment. And now it's a pleasure and honor for me to present you at least two examples of microelectronic research and development in Saxony and especially at the Fraunhofer IPMS. So the first demonstrator I want to show you is this intelligent sensor ring you can see here, and this is directly implemented into the structure of a ball screw. These sensors are made to, let's say, make older machines subsequently smart for Industry 4.0, so that can be retrofitted. The technological challenges for this demonstrator and thus the decisive developments of Fraunhofer would be, for example, a wireless data transfer and also a wireless power supply. You can see that, for example, only below, sorry, you have to look there. Below is the control unit, and the sensor ring here communicates via this slit with a control unit. Another challenge is also a very flexible integration into an already existing system. That means, for example, that you have to bring this round shape here around. And for this development, Fraunhofer developed, for example, this kind of really flexible integration or interconnection that connects the several chips that are put in there, for example, to measure temperature, to measure force, or to measure vibration. That this can be connected together and then really can be brought into this kind of round shape. So you can have a closer look. I have two, if you want to have
this
also there and there. Yes, so this flexible interconnection. Application scenarios.
Is it mainly for maintenance, or?
Yes, so application scenarios could be a condition monitoring, preventive maintenance, and also adaptive process control. So you can use it for everything. Overall, this demonstrator represents a cooperation of 4 Fraunhofer institutes at the state level of Saxony. So they all worked here together. One developed the sensor, one the integration, and one this flexible interconnection.
Excellent.
Right.
And when did you stabilize this technology? When did you stabilize this technology and this approach?
I think this is already now available for research, not for research, so really on the market, so that you can
so you are
use.
transferring
Yes,
now.
we are already transferring.
And do you experience already demand from the industry?
Yes, there's a lot of demand with regard to retrofitting old machines and really to go for industry 4.0.
I think
Yes.
our question is: the research was a request from the industry or an initiative from the Fraunhofer?
Both. So of course we are only acting on
this is a
requests
permanent
from
discussion.
industry. Yes, that's a permanent discussion. Yes.
I think this is the power of this model.
Yes. Okay. I would surely go on the other side, so I would hand over to the second research field I want to present now. This is the process and device development for advanced CMOS and next generation computing technologies. I think you may know that all microchips are based on the material silicon. Of course, not in this version. This is just the raw material sand. But from the sand, then pure silicon blocks could be refined. So that would be pure silicon if you want to have it. It's not that big. And from this silicon, then for the real microelectronics, monocrystalline silicon is grown. And this is an example.
For euro.
This one for euro. This is the example. So an end of such a monocrystalline silicon. It's a silicon ingot. It's really heavy. The properties of this silicon is that it's completely defect-free, homogeneous, and so let's say it's really clean. From such a kind of ingot you would get a wafer, silicon wafer with a size of 150 millimeter.
It would be slices of this one.
Yes, they are sliced.
Because it's super concentrated heat.
Yes.
It's purified.
It's really purified, and you can only make microchips on really purified silicon. Of course, for the advanced technologies, you need wafer sizes like this. So this is 150 millimeter, but all at once CMOS is done on 300 millimeter wafer size. So if you want to have it in your hand, so that's wafer size. The companies like Infineon, Bosch, and Global Foundries here in Dresden are working on. ST Microelectronics in France, future I think also Intel and ESMC, of course, are working on this wafer size. And Fraunhofer in Dresden also runs clean rooms for this wafer technology, and that are the only ones in Germany. So we have here in Dresden the only research clean rooms working on this wafer side. And and with our advanced infrastructure, we support the named companies to develop innovative microchips, more power efficient microchips, greener microchips. But we also support to improve the microchip production and manufacturing itself. So that is the main focus for our research here. For the developments for next generation computing, however, so for example, neuromorphic computing or quantum computing, that are two topics we
below 9 nanometer.
Yes, you need 9, but you don't need only the advanced for neuromorphic. For neuromorphic computing, you mainly need memories. So that is one thing that you really need, memory technologies. These topics are mainly executed in huge European consortia, and also we at Fraunhofer IPMS are cooperating very intensively with CLAT and with IMEC. And next to the joint research projects, we even established an exchange of researchers with CLAT in Grenoble. And yes, this exchange of researchers is needed with the goal to support several technology developments from each partner and then combine them together in one system. For that, it's needed really to have a research exchange. And here we have one of our...
And you're working in mixed teams, or?
Yes, in mixed teams, yes, right. So here's one of our researchers who visits regularly CLAT in Grenoble. And Annika will now tell you something about the challenges to build these combined microsystems.
So I'm Annika Vandersleven and I'm a PhD student at Fraunhofer IPMS. And
Ça c'est la technologie.
Adaptive AI.
There's some research necessary.
that's maybe one more reason to build synergies, to combine infrastructure and individual competences. And in microelectronics it's a little bit special, so even the smallest impurities can have a detrimental effect, so it can lead to short circuits which render the intended chip completely useless. So that's the reason that we need high purity standards in production and even for the exchange of wafers. So like during projects like Prevail, where we have a wafer exchange, to combine the technologies on the same wafer, we need a special exchange procedures. And my thesis focuses on the analysis of the tiny amount of impurities that we can have during the production, and also the development and integration for the use of new materials and the necessary safety measures. And for this reason, I had the pleasure to have 2 research days at CLAT in Grenoble. So here's a part of the team as well.
Ah, c'est pour vous, c'est le...
Yeah, that was the present after my first day there. So
A farewell,
ministre.
a farewell gift.
Yes.
Jacques est le ministre.
Yeah. And so together we are working on the comparability of this highly sensitive analytical technique on the one hand, and also on fundamental research for new materials. So
How long did you stay?
4 months each stay, so in total 8.
And are you returning to Grenoble?
It's not planned for now because I'm at the end of my PhD.
Ah.
So you will become researcher now?
Yes.
And we're
then we
here?
will see. Yeah, for the beginning here and hopefully
team.
still working close together with the CLAT.
And how many researchers in total are part of this program, I mean this partnership?
It's not a totally established now, but we try to exchange as much as possible. So we had already some.
You have a core team and in fact you have partners and
Yes.
collaborations.
Yes. And of course it's also up to us PhD students to say we want to go, we want to exchange the knowledge.
And how do you source your PhD, if I may say? Because it's a partnership with some universities.
Yes, of course, you just bring out a position and then hopefully you have a lot of really good applications that you screen through. But normally we are quite successful here, and of course, you try to advertise everything at the universities.
And where were you at the university before?
before at the University of Applied Science in Aachen, so in the southern Germany, so not Dresden. But for the exchange, it was maybe more important that I'm really working on this exchange topic as well. So we need this to develop for the foundations for the further innovations like neuromorphic computing and quantum computing, and also to ensure the feasibility for industrial application. So we have to keep this in mind as a research institute that we also want.
And also French researchers.
Yes, we also have French researchers here. We have a total of more than 30 different nations represented. So I would like to guide you to the next station.
Sure.
Thank you so much. Good luck.
Thanks.
Thank you. Thank you. Say hello to everybody.
I will.
Nice to meet you.
Dear Presidents, Monsieur le Président, Mr. Steinmeier, thank you so much for taking the time to discuss the important strategic topic of AI with us today. And I would like to move straight from symbolism to strategy and ask both of you to quickly articulate your strategic priorities for AI in Europe. I believe we have a strong imperative that is at play here, and I would like both of you to give us a concise statement on that topic, please.
You know, we renounce to any longer statements because we are very limited in time and we are trying to learn from you. So therefore, thank you first of all very much for hosting us here in the Fraunhofer Institute. Secondly, thank you for giving us an insight in your research you are doing here in this site, and I think it's our common impression that what we saw is really cutting edge research, and I think we are arriving here with one main question, knowing that microelectronics is the key for, let's say, competitiveness in the future in Europe. It's the key for sovereignty, economic and technological sovereignty in Europe. So therefore, we know it's the key competence on the one side, and I'm afraid we have to admit we are behind others. And the main question is if there is a chance to catch up with some of our important competitors around the world, be it the US, be it China, or others. And my question is, what do you expect from politics? What do you expect from business and companies to keep this chance alive?
Thank you, Mr. President. Yeah, Walter. No, thank you very much for taking this time for us to educate us. In a nutshell, to give our strategy on AI, we launched in 2018 a first strategy that we refreshed a few months ago. And I think when we look at the whole picture, I totally agree and concur with the question raised by my good friend, President Steinmeier. But we have obviously our ability to develop and create more and more LLMs and not to be dependent on just American and Chinese ones. We have some competitors, but how to do more? Second, the question is how to multiply the implementation, the right use of artificial intelligence in different sectors. So it's for me verticalization in mobility, in healthcare, and so on, where it's a critical race. But for me, more than that, when we look at the bottlenecks today and probably the European weaknesses, it seems that if we want to deploy and create more, we need a lot of computing capacities.
Yeah.
So it means chips, and this is why I raised the question here, how fast will you deploy this 7, 9 or even less nanometers chip, because at this stage it seems that we need the Taiwanese and the Americans to help us. So what's your view on that, and how to have a more European approach on the chip and semiconductor sector, because it's one of the critical parts. Computing capacities, so how to create more data centers and to deploy more data centers everywhere. Today in Europe we have something like 3% of global GPU. Our objective is at least to have 20, but we are very far from this target now. How to do much more. And the final bottleneck probably is energy, because the more we will create computing capacities, the more we will consume energy. And this is where we can find solution. And I think we have quite now solutions for low carbon and pilotable energy. And I think if Europe has a clear electricity strategy, it's absolutely critical for indeed artificial intelligence. Our strategy is to make it at European scale, but on the critical, on top of the question raised by President Steinmeier, my additional question would be indeed on chip and computing capacities, and how to be sure that the Europeans, given innovation and investment effort, could be in the race.
Thank you so much. I would like all of us to face reality in one way, which is that we didn't do so well in prior technology waves. We didn't do well in the internet. We didn't do well when it came to cloud and on mobile. We all believe and agree that AI can be a huge accelerator. It is a transformative technology that speaks to European strengths in the verticals. And I would like to start out with you, Cedric. You are representing Siemens, which is one of the oldest and most influential German conglomerates in the manufacturing and the industry space. What are your priorities when you're thinking about AI?
Yeah, first I need to say I'm half French, half German, so two presidents at the same time is very rare, so I'm very privileged to have you here, but old is not a differentiator. If we go to the AI models,